Okay, AP Environmental Science. I want to take a few minutes and I want to talk with you about population growth. You've already learned a few things about that. There are a couple of different models of population growth that we can look at. If a population has plenty of resources and unrestricted breeding, over a certain period of time they can undergo what we call exponential growth. When you see a graph of exponential growth, it will tend to have this distinctive shape. It looks a little bit like the letter J, so we sometimes call that a J-curve. So a J-curve represents exponential growth. Now, over the long run, different models can happen, but many different types of living organisms over the long run do not continue to follow exponential growth. They shift into what we call logistic growth. As resources become tighter, the growth rate can level out and you can end up with a more stable population. So when that happens, you have the high growth rate at first and it levels out toward the end. So this represents what we call logistic growth. And when you see a graph of logistic growth, it has a shape a little bit like the letter S, so we call it an S-curve. So exponential growth is represented by a J-curve. Logistic growth is represented by an S-curve. Now I want to point out something to you here, that over a short period of time, this S-curve actually looks very similar to that J-curve. So if we were to just look at the bottom of the graph, this portion of the graph looks very similar to this portion of the graph. Somewhere along the way you make that switch. So if we start making predictions based on an exponential growth model, those predictions will probably be fairly good over the short run. But if we go for long time periods out, we may switch from an exponential growth model into a logistic growth model. So most of our predictions are limited in the range that we can make for time for the population. I now want to focus on numbers, and we're only going to worry about putting numbers with making predictions based on exponential growth. Now, to really deal with that, we would have to deal with exponential equations. You can write exponential equations lots of different ways. That's a common way to write an exponential growth equation. Some of you are no doubt intimidated just by looking at that. You should have learned about that in your math class, but AP Environmental Science, we don't deal with exponential equations. We don't actually have to solve those. If we did, we would have to use logarithms, and I know some of you are even more intimidated by the phrase logarithm. So even though the real equation here for exponential growth is this, we're going to ignore that. We're not going to solve. We're going to use an approximation to solve problems using exponential growth. And I want to give you that formula that we're going to use to do that, and then give you some examples of how to use it. All you're going to use in order to solve problems for exponential growth, we're going to use what we call the doubling time equation. It's really the doubling time approximation. And what that says is that the doubling time is approximately equal to 70 divided by the growth rate as a percentage. Now, if I just say that, that may not make sense to you, but I now want to give you some examples to help you understand that. So, let's go back and say that we have some data from 2006. And in 2006, let's say that the population growth rate was about 1.3%. The world's population was growing about 1.3% a year. So what this is giving me the population growth rate. How long would it take the world's population to double? So if we want to find the doubling time, it's a pretty simple approximation. We're just going to take 70 and we're going to divide it by that growth rate. So you would, hopefully on the AP test, you'll have nice numbers, more like 2%. It's easy to divide by 2. But here we have an ugly number, 1.3. So I'm going to do 70 divided by 1.3. And I get 53.8. So this would come out to be the doubling time. 70 divided by 1.3 is 53.8 years. It would take 53 years for the population to double at this rate. So, the first question is, how long would it take the world's population to double? 53.8 years. The second question is, when would this doubling occur? Well, that's 53, almost 54 years later. So 54 years after 2006 would be 2060, or maybe just before 2060, 2059. Hopefully that makes sense. We will go back in a minute and talk about how even with this uglier number, if you had to do this, you can do this by hand. Okay, so we'll look at that in a second. But the key thing that I want you to see so far is we have a simple equation to estimate the doubling time. It's an approximation. Okay, look at number 2. If the population growth rate continues at 1.3% and you are 17 years old, how old will you be when the population doubles? Notice that the population growth rate is the same as before. Therefore, the doubling time is going to be the same. We would use the same doubling time equation. It would still be 70 divided by the growth rate, which is 1.3, which is still 53.8 years, about 54 years. So all they've done is they've added to make you go a step further. So if you're 17 now, how old will you be 53 years later? You'll be 70, or 54 years later, you'll be 71. So let's just say that's 54. So 54 years later, you'll be 71 years old. So there's just an extra step. You're finding the doubling time, but then you have to add it to your current age. Same basic idea of a problem. Okay, one last example. The doubling time for the world's population is 56 years. What will be the growth rate over this time? I want you to notice, here they are not giving us the growth rate. What they are giving us is the doubling time. We're still going to use the same relationship, but we just plug it in a different way. So here I'm going to put 56 in for the doubling time, and that's going to be 70 over R. So this will involve a little bit of algebra, but it shouldn't be anything too difficult. So all we're going to say here is that the doubling time is 56, and that is 70 over R. So we just want to solve for R. Well, I don't want R on the bottom. So to get R off the bottom, I multiply both sides by R. So now I see 56 times the growth rate is 70. So then to solve, I divide by 56. Now again, if you do have a handy calculator, you could use that in this case. You could come over here and you could say 70 divided by 56, which in this case comes out to be a nice pretty number, 1.25%. That's the growth rate. At this point, I hope you have grasped the equation. There's only 2 variables in the equation. I could give you either variable and ask you solve for the other. So if I give you the growth rate, you can solve for the doubling time. If I give you the doubling time, you can solve for the growth rate. The last thing that I want to do in this video is I want to go back and I want to talk about doing these problems by hand when you are not allowed a calculator on the AP exam. So let's take a look and let's go back and let's try to do this, and I want to teach you some math techniques to be able to do it on paper or in your head. So this same problem that we did before, we're going to do again. The doubling time is 70 divided by the growth rate. So here the doubling time is 70 divided by 1.3. That's exactly what we said before. Now before we used the calculator for this. Well, if we don't have a calculator, you could go through and you could do old school long division. So in this case, I have 70 divided by 1.3. You can move this decimal over a place, so you can move this over a place, so it's really 700 divided by 13. Well, you could say 13, let's try 5. 5 times 13 is 65. 65. You could subtract, you could bring that down. Okay, 13 will go into 50. Ooh, almost 4 times. 3 times. 39. And you can keep going. So now we have 110. 13 goes into 110 8 times. So that'd be 104. And it's going to keep going, but you can see I now have my 53.8 years. You can do that up by hand. Now you can also use some tricks. One thing that I like to point out is that it's much easier to do math problems by hand if you use fractions instead of decimals. In my opinion, fractions are a superior system. Let's look at this same problem one more time, but let's try to do it by using fractions. So here what we had was the doubling time, we were going to do 70 divided by 1.3. Let's think about what that 1.3 means for a second. 1.3 in this case is the same as 13 tenths. So we really have 70 divided by 13 tenths. 70 divided by 13 tenths. But when you divide by a fraction, you multiply by the reciprocal. So again, here we get 700 over 13. Now, that leads us back to the same division problem that we had before. So in this case, the fraction doesn't actually work out to be any easier. In some cases it does, because you can do a lot of simplifying in fractions that are not immediately obvious with the decimal. But if you have to work it out by hand, just take the time, do long division like you know how to do, or use fractions to help you. Okay, let's now go back, do one more. So here we knew the doubling time and we wanted to find the growth rate. So the doubling time was 56 years. We wanted to find the growth rate. So before we did it with a calculator, now we're going to do it without the benefit of a calculator. So we're going to say the doubling time is 70 divided by the growth rate. We know the doubling time is 56. That's 70 divided by r, just like we did before. Multiply both sides by r. 56r equals 70. Divide by 70. And here, I'm going to look at this, divide by 56. I'm going to look at this as a fraction. You should notice they're both even numbers. 2 goes into this 35 times. 2 goes into this 28 times. Hopefully you now notice that 7 goes into both of these. 7 goes into this 5 times. 7 goes into this 4 times. So it's 5/4, 1 1/4. So the growth rate is 1 1/4. 1 1/4 is 1.25. So really this division, if you understand fractions and simplification and you do a little bit of practice, is not much harder than typing it in your calculator. I prefer that you look at it as fractions this way and simplify it. If you really hate that, you can still do this with classic long division. I'm not going to do it that way, but you can. Long story short, you need to know your doubling time equation. This is for when we have an exponential growth and that growth rate is going to hold, and we're going to estimate that doubling time is 70 divided by r.